Hey folks, Mr. Ray here again. We're going to continue on in advanced functions with our next lesson in logarithmic functions. Previous lesson we reviewed the exponential functions and looked at, well, what would the inverse of an exponential function look like? We looked at the properties, and I kind of broke the news to you that the inverse of an exponential function is a logarithmic function. Okay, so we're officially introducing that as it's named this lesson. So here's the definitions. Exponential function is a function where whose value is a constant raised to the power of an argument or variable. So like y equals 2 to the x or 4 to the x. Okay, so the variable is the exponent or the power. Okay, with the logarithmic function, here's the official way of writing it. Y equals log, and you see a little b there. Okay, that's written as base, log base b. So whatever that number is would be the base of x. So the way I would read this, y equals the log of base b, log base b of x. Okay, now if you were to write this, if we go back to the original exponential equation, it looked like this. Okay, but remember the inverse. Inverse, we switch x and y variables with each other. So the y here becomes x, and the base stays the same because it's not x or y, and the exponent now changes to y. So if you were to rearrange this, you would basically get y equals log base b of x. So if you're thinking about it, what we're trying to solve here is what is the exponent, what's the exponent that we apply to this base that gives us this number. Okay, it's really important to understand whenever you're getting a log of something, you're actually finding the exponent that you would raise a particular base to that gives you that number. Okay, so this is a really critical message. A log is an exponent. So it's always really helpful to know that, because sometimes it can get lost on you. What am I actually trying to find here? So just remember, a log is an exponent. Okay, so here's a reminder of the graphs we did last lesson. Here's an exponential function, y equals b to the x. This would be the function x equals b to the y, or in other words, y equals log base b of x. Okay, so just like exponential functions can have all sorts of bases, you could put any number there, except we kind of said anything that's positive except for 1. Same idea with this. We're going to see the restriction on the same restriction on the base for the logarithmic function. Okay, so I'll just go through this, make sure I cover everything. The value of log base b of x is equal to the exponent, so here we go again, to which the base b is raised to produce the value x. Okay, and we're going to try this out this lesson. We can take an exponential equation and turn it into a logarithmic equations, and vice versa. Take a log equation, turn it into exponential, and sometimes that's actually a very good strategy. Sometimes changing it back and forth can actually get you the answer very quickly that you're looking for. All right. So this, I've already talked about this. The base for both exponential and logarithmic equations has to be positive, but it can't be 0, and it can't be 0 because it has to be positive, but it can't be 1. So anything bigger than 0, but not 1. Okay, and the other restriction here is that I think this is actually wrong here. The x for the logarithmic function can't be 0. You can't take the logarithm of a negative number. Okay, but your result here could be negative. You could have a negative exponent, if you remember. Okay, Now the reason why we don't do 1, I mentioned this last time, same reason that we can't have a base of 1 for exponential function. It's because when it is equal to 1, y would have an infinite number of solutions and therefore not a function. Okay, remember, a function that would fail the vertical line test. All your points would be along the line x equals 1. Okay. Now we have a couple of special logs, one I mentioned here. So we have a common log. So a common log means it has a base 10. Okay, so I'm going to write it here because I have another one for you. So common log or logarithm, the base equals 10. Okay, and what we do, since this is so popular, so common, we actually drop the base from the log. So this means that if you see something like the log of x, it actually means log base 10 of x. Okay, and that's what your calculator actually does on the log button. It's actually using base 10, even though it doesn't show it on the button. So that would be called a common log. We also have something called a natural log. And this is where the base is equal to, it's actually a variable that we use a lot in math and science. We call this variable Euler's constant, or Euler's number sometimes. And that number is approximately 2.71828. Keeps going forever. It's a lot like pi. It's probably the second most popular number in math, constant in math besides pi. So that represents that number there, Euler's constant. So kind of wrote where I wanted to write here. So if we had log base e of x, we tend not to write this. I don't think I've ever seen it written this way. So we actually replace with log base b into something called a ln, ln, and it would be just ln x. Okay. You also have a button on your calculator for natural log. So the ln button would be the same as log base e. Okay. And we have that because it's a very common calculation that we do, just like log base 10 is. Okay. All right. So a couple little exercises here. We're going to, right now these are written in exponential form. We're going to change it into logarithmic form. So this is actually quite easy. It can be a little strange at first. So if you remember, if you looked at this, the first thing I would look for is the base. So the base is, it's the base of the power that's written here. And then the exponent here, this would be, this is your exponent. I'll just write it exp, and this is the result. So if you think about it, the base to the exponent gives the result. So when I write this over to logarithm form, I want it to look like this. I want it to be, remember the log is an exponent, so it's got to be exponent equals log base b, and the base b is the same b as over here, of the result. I don't expect you to think about it this way all the time, but at least remember that the exponent is how we're going to start this equation. So this is going to be written as the exponent is the log base b, which is base 2, of the result. Okay, so as long as you can figure out where the base is and where the exponent is, you should be good. And what the result is always goes, you're taking the log of that number. Okay, so let's try it with this one here. So again, I want the exponent. So here the exponent is 3. So that's the logarithm. So 3 is the logarithm of, logarithm base here is n of the result, which is m. Okay. Next one here, we've got a negative exponent this time. 3 to the negative 2 equals 1/9. Remember that from grade 10 and 11, I hope. Okay, so again, writing it as a logarithm, we want the exponent. Exponent is negative 2. That's equal to the log base 3 of the result, which is 1/9. Okay, so hopefully that makes some sense. Now we're going to go the other way. So that now it's written, these are written as logs. I want to change it around into exponential form. So this one should be probably more straightforward. This time it's the result is equal to the base to the power of the exponent. Okay, now, oh, this is evaluate. My mistake. Okay, so we're evaluating these logs. Now, when I read this, it's important that you read this so you can understand it. So I'm looking for the log base 3 of 81. What does that mean? It means I'm looking for the exponent that when I apply it to the base 3, I get 81. So this is basically saying 3 to what number gives me 81? What's the exponent that I apply to the base 3 that gives me 81? So, I mean, you could just play around with this. 3 times 3 is 9. 9 times 3 is 27. And times another 3, that's 81. Well, so that's 3 to the power 4. So I actually know the answer is going to be 4. But I want to show you a way that you can do this that makes some sense. So I'm going to rewrite this still as a log to begin with. Now what I want to do is, I'll put in brackets here, I want to change 81 to a 3 to a certain power. So 3 to what power gives me 81? That's 3 to the power 4. Okay, so now when I read this question, it's going to sound really silly when I read it. So the question is, I want to know the exponent that I apply to the base 3 that gives me 3 to the power 4. So basically 3 to what power gives me 3 to the power 4? Well, obviously the answer is 4. So if I can rewrite the question in this form so that both of these bases are the same, then my answer is whatever that exponent is. Okay, we'll try it again with this one here. So this is saying log base 2 of 1/8. So it's saying, okay, the base is 2. So 2 to what power gives me 1/8? So obviously this can't be positive because 2 to the power 1 would give me 2. 2 to the power 2 gives me 4. It just keeps getting bigger. So I know it's going to be negative because negative exponents gives me fractional numbers. So I'm going to rewrite this, log base 2. Now I want to write 1/8 as 2 to the power, just like I kind of did here. So if you think about it, you can almost just look at the 8. I know that 8 is 2 to the power 3. So 1/8 would be 2 to the negative 3. Okay, and now I've got the two bases. So I'm asking myself the question, what exponent do I apply to the base 2 that gives me 2 to the power of negative 3? Well, that's obviously negative 3. Okay, and then this last one has a decimal. This is log base 10. So remember, we call that the common log. So this is actually saying 10 to what power gives me 0.01. And again, you expect this to be a negative answer because 10 to the 1 would be 10. 10 squared is 100. So I have to go into the negative territory. Okay, so if I rewrote this as log base 10 of 10, so if I think about it, how can I represent this as a 10? Well, that would be 10, that would be to the negative 2, because 10 to the 0 would be 1, 10 to the negative 1 would be 0.1, 10 to the negative 2 would be 0.01, so that's negative 2. And you can always play around on the calculator with these if you're not sure. So again, I've got this matching set of bases. So my answer is the exponent, because this is really saying, what's the exponent that I apply to base 10? That gives me 10 to the power negative 2. So both of these numbers are bases, so if they're the same base, your answer will be that exponent. Now, I'm not saying you have to do it this way. This is a nice little option to understand it better, I think. But if you could have done this one without just saying, oh, 3, it would be 3 to the power 4, so therefore my answer is 4, you wouldn't necessarily have to do that step. Okay? It does help at the beginning when you're getting used to logarithms. All right. Here's the question I thought we were on. This is something in logarithmic form, and I want you to rewrite it in exponential form. So remember, exponential form basically looks like the base to the exponent is equal to the result. Okay, so when I'm thinking about base, well, where's the base in this equation? That's the easiest thing to find. That's the little subscript there beside the log. So I know it's going to be 4 to a power. Now the exponent, remember, is the log. So the log is what's on the other side of this. So it's 4 to the power 3 is equal to the result 64. Okay, so that's just switching around the equation to be in exponential form. Now this one here, remember, so we got y equals log x. Well, you can't see the base there, so what's the base? So remember, if there is none there, the base is 10. Okay, so I can start going. So I want the base is 10. The exponent is the result of the log, is the log. So that's 10 to the power of y is equal to x. Okay. Now, this section here, like so far most of the questions we've done had nice integer answers, sometimes positive, sometimes negative, but that's never going to happen all the time. So if I had something that doesn't come up with a nice number, and we're actually going to show how to do this exactly in the next lesson, so we're just looking at kind of an estimate, approximate value for each of these. Okay, so log base 2 of log base 2 of 10. So I could start with things that I know are true. So if I'm looking for certain powers, I would know that log base 2, say, of 4. So what exponent do I raise the base 2 to get 4? Well, that's equal to 2. Okay, so that 4 is much slower than the 10. So I keep going. So what's the next number that would be a nice integer? Well, that would be log base 2 of 8. Okay, so 2 cubed gives me 8. So the log base 2 of 8 is equal to 3. So 8 is still less than 10. So what's the next one? Well, the next one would be 16. Log base 2 of 16. So that would be 2 to the power 4, so the log would be 4. So you can see that the 10 is somewhere between the 8 and the 16. Okay, and I'm not going to spend a lot of effort on this. It looks like it's going to be closer, the result would be closer to the 3 because 10 is closer to 8 than 16. So I'm just going to take a rough guess and say log base 2 of 10 is approximately equal to, I'm going to say 3.2. I don't have a lot of proof or math process that says why I think that. That's just my intelligent guess, hopefully. Okay? Let's try the same thing with this log of 2500. So again, this is a common log. So base 10. Okay? So this, if you wanted to, at the beginning, you could write as like that so you understand it. Okay, but after a while, hopefully you see it as base 10 without even thinking about it. Okay, so what log base 10 numbers do I know that work? Well, I know for 100, log base 10 of 100, that would be 10 squared would give me 100, so the log of that would be 2. If I go one higher, so if I multiply by another 10, that would be 1,000. Log base 10 of 1,000, that's equal to 3. Okay, so 1,000 is still less than 2,500. So the next one would be log base 10 of 10,000. So that would be 10 to the power 4. So the log is 4. And you can see, well, 10,000 is a lot bigger than the 2,500, but bigger than the 1,000. So again, my result is going to be somewhere in between here. So I'm going to, again, it looks like it's a lot closer to the 1,000 than the 2,500. Now it's not linear. I can't just say, well, it's going to be, exactly 20% higher than this, or so. I'm not going to put a lot of thought into this. So I'm going to say log. This time I'll just take out the base 10. Log 2,500 is approximately equal to, and again I'm going to say like 3.2 again, just because it is a lot closer. Not much more to it than just an intelligent guess. Okay, so that concludes the lesson. So if you think about what we've done, we looked at the form of exponential versus logarithmic. And remember, the most important thing to remember, a log is an exponent. Okay, so we learned about common log, natural log. Those are just very specific bases that we use a lot. Okay, then we learned how to convert back and forth between exponential and logarithmic, and then how to start evaluating logarithms. So we only really officially got answers for nice integer values, and then we did an approximation for one that wasn't a nice integer answer, and you can see that it's, hopefully we have something we can use, and that's going to be our calculator with a couple new formulas. So that's what we're going to do next lesson. We're actually going to look at some laws for logarithms that are going to help us evaluate a little better, and also a way that we can use our calculator to get any logarithm. Okay, so got some homework at the bottom. Please try that. Get very comfortable with knowing what logarithms are, how you can change it back and forth between the two different forms, and how you can have a couple strategies like we used here to evaluate the logarithms. Okay, that's it for today. Have a great day. We'll see you next lesson.